Ladies and gentlemen, we will continue to discuss with the uncertainties involved in analysis and design, which we continue in the last lecture. In the last lecture we said that the cumulative damage accumulated is given by equation 4, where the expected value of n tilde ADA will be the expected number of cycles, in fact I should say number of stress cycles with amplitude between A and A plus dA. Of course, during the time t. Therefore, d of t can be expressed as Vx plus 0 t Fxp A dA by n of A, which we said equation number 5, or we can say equation number 5a, and so on. We already know the value of Na is given by the transformation from the first equation, stress range to the power m by k. In my case the stress range is 2a to the power m by k. Substituting for Na in equation 5, I get d of t as V x plus naught t integral 0 to infinity 2a m by k f x p a d. Let me call this as equation 6. Now, having said this, let us look at this equation 6 and substitute for these variables and try to evaluate this function for a variable range from 0 to infinity in the integral domain. For a narrowband process, which is Gaussian, f x p a, that is this value, can be given by a by sigma x square exponential of minus a square by 2 sigma x square. I call this equation number 7. So, I know the value of f x p a given by this function if it is a narrow band process which is having Gaussian distribution. Substitute this value of f x p a in equation 6 for the variable here and then try to find out the cumulative damage dt from expression 6. So, I should say substituting 7 in equation 6 we get d of t v x plus naught t. I am rewriting this slightly in a different manner. I have 2a raised to the power m here, I have a also here. I rearrange them slightly and write it in this form here as you see in this expression, 2 to the power of minus m, that is 2 power m 2 power minus m, k, I already have k here which is a material constant, and sigma x square I already have it here. Now, I have a power m and a, I put it inside, I can remove this flower. Exponential minus a square by sigma x square of d. Now, integrating this equation from the domain 0 to infinity, I can rewrite this equation as d of t Vx 0 plus t to root 2 sigma x m, that should be rather the power of the whole variable, by k gamma function of 1 plus m by 2. Now, where this is a gamma function, the value of these functions are available in the standard tables, but for the sake of yours let us say gamma of n plus 1 is simply given by n factorial, where n can take any value from 0, 1, 2, etc. So, let me call this equation as equation 8. Now, in this equation I got the value of t which is nothing but the lifetime estimate of the structure based on the cumulative damage caused because of exceedance of stress values in a stress range of 2a. So, it is a fatigue damage. So, I am interested in finding out the life estimate of the structure based on the cumulative damage caused because of stress exceedance beyond a threshold value in the range 2a in a period t. So, from equation 8, life estimate can be computed as K Vx plus naught of inverse, I am interested in finding out T, divided by 2 root 2 sigma x m, gamma function 1 plus m by. That is, in this equation I substitute d of t as unity, that is the damage. I call this equation number 9. V of x plus naught for its inverse is otherwise addressed in the literature as Tz, where Tz is called 0 mean crossing period. Therefore, T can be given as K Tz by 2 root 2 sigma x m gamma 1 plus m by 2, where m and k are material properties. So, this is how one can estimate the life estimate of a given system when subjected to an accumulated damage caused because of exceedance of stresses or stress cycles, which we call as fatigue damage. So, this is the uncertainty which we are talking about in the lecture in the last presentation. Having said this, we also said when we discuss about the analysis and design of offshore platforms, there are uncertainties associated in calculating even the design checks. So, let us take an example of design check done on offshore members. As I said, in design we actually do not find out the cross sectional dimensions of the members. We do not find. What we do is we check the adequacy of the sizing. So, the member dimensions are really known to me, I only just check whether they are adequate or inadequate. So, we will take up an example using a specific international code. We will solve this example and show you how to calculate the check for design adequacy. This is just an only introduction for people to understand this course. If you want to really look at the detailed design procedures, you must follow additional courses available in NPTEL on design of offshore structures. So, I have an example 1. The question says examine the safety or I should say adequacy of the cylindrical member using ABS code. Given data are the following: D, which is diameter of the member, we say it is 600 mm. T, which is thickness of the member, which we say 12 millimeters. Young's modulus of the material, yield stress of the material, length of the member, that is 4000 millimeters, effective length factor, which I call as K, is 0.8 and subjected to an axial force, which I say the axial force P axial is 1 meganewton. So, I have a cylindrical member whose thickness is 12 millimeter and the external diameter of the member is 600 millimeters. The member is having effective length factor as 0.8 and the overall length is 4000 millimeters. The material characteristics in terms of Young's modulus and yield strength are known to me. I want to check whether the member is adequate to carry the axial compressive force of 1 meganewton. So, ladies and gentlemen, you will agree that in design the member dimensions are not arrived, the member dimensions are already prefixed. We only check the adequacy whether this is sufficient and we use a specific code which I will do now and demonstrate for you. So, the code which I am referring in this example is ABS which is guide for buckling and ultimate strength assessment for offshore structures. ABS 2008. So, now we will solve this problem. Step number 1, we know the data given to me are the following. I will work out basic design parameters. That is what I am going to do in step number 1. So I will find out the cross sectional area, which is nothing but pi d square by 4 d outer minus d inner. So let us say 600 square. The thickness of the member is 12 millimeter. So both the sides 24. So I should say 576 square. So 600 square minus 576 square into pi by 4, I get 22167.08 millimeter square. Now I can find the axial compressive stress, which is nothing but P by A. So P is given to me as 1 mega Newton, so 10 power 6 Newton, and 22167.08, which is 45.11 Newton per mm square. Now we find the moment of inertia, which is pi by 64 d power 4 minus di power 4. So in my case pi by 64 604 minus 576.4, which is 0.96 into 10 power 8 mm to the power 4. I want to find the radius of gyration, which is about the minimum axis. Being circular member, it is going to be uniform about xx and yy, which is going to be I by A, which is root of 0.96 10 power 8 by area is available here. So 22167.08 the square root, which comes to 207.93 millimeter. Now the effective length of the member is going to be 0.8 of 4000, which I call L as 3200 millimeters. We also now work out polar moment of inertia. I call this as I naught, which will be given by pi by 32 d outer minus d inner, which is pi by 32 600 minus 576 . (1.92 10 power 9 mm power 4). I also work out Sen-Venant's constant for the tubular member given by K. This is available in ABS, Guide ABS 2008, table 1 on page 7. The equation is available. K is given by pi by 4 d minus t the whole cube of t. I substitute now, so pi by 4 600 minus 12 cube into 12 which is again 1.92 into 10 power 9 mm to the power 4. Step number 2, I want to compute the Euler's buckling stress sigma E. This is given by class 3.3. So, now pi square 2 into 10 power 5 by KL, already we said it is 0.8 of 4000, and RY we already have 207.93, the square value of this. So, calculate this, we get 8334.2. That is what we call as Euler's buckling stress, so many Newton per mm square. We also compute the warping constant, which is given as gamma. Generally this is given as 0 for tubular members. Also dcs, that is the distance of centroid and shear center along the major axis, which is also 0 for the present problem because the section is symmetric. Now we shall establish what we call the compact limit of the given member or the section. Now you may wonder why one is interested in estimating the compact limit of the section. Suppose if the compact limit is established, then the section will not undergo buckling. So yielding precedes buckling. However, for non-compact sections, local buckling should also be considered. That is the catch here. So it is important for us to establish whether the given dimension of the member is a compact section or a non-compact section. If the given member is a compact section, then yielding will precede buckling, no local buckling will occur. If the given member is a non-compact section, then I must include local buckling also while checking the design adequacy for the given member under the axial force. So how to check the compact limit of a given member? So referring to table 1 of ABS 2008, we should calculate a ratio d by t to check whether this is less than or equal to E by 9 sigma naught. Let us say in my example, for my case I say d by t is 600 by 12, sorry, which is 50, and E by 9 sigma naught 2 into 10 power 5 by 9. Sigma naught is the axial stress which we have calculated in the first step, which is the permissible yield value, which is 240 in my given problem, which is 92.39. Now d by t is less than E by 9 sigma naught, hence the section is compact. So what is the advantage? Once I say the section, given section is compact, yielding will precede buckling, local buckling need not be considered in my design adequacy. Is that clear? Taking this forward, step number 3. I want to determine the adjustment factor for computing the maximum allowable strength. This is where we are trying to compute the design adequacy. The maximum allowable strength cannot be considered as it is. I must multiply this with what we call an adjustment factor. These are all the level of uncertainties introduced by different international codes while executing the design checks for any offshore member. For offshore members, under static loading, the utilization factor is given as 0.6 of psi. When you talk about the storm weather or the storm case, there is a rough storm case, then this factor is increased to 0.8 psi. Where in this equation psi is called the adjustment factor. So these conditions are available, wide class 1.9 of ABS 2008 on page 11. So psi, which is the adjustment factor, is given by simply 0.87 if sigma EA is less than or equal to PRA, PR sigma naught. If it is not satisfied, then it is given by 1 minus 0.13 square root of PR sigma naught by sigma EA for sigma EA exceeds PR sigma. So, we must know the value of PR, the value of sigma EA, and of course, we already know the value of sigma naught for this given section. If we know these two values and check whether this condition or this condition is satisfied in the given problem, substitute and find out psi, which we call as adjustment factor. Sigma EA is called the elastic buckling stress. P is the proportional elastic limit, which is a material property, and sigma naught is the yield stress, which I know for the given problem. You can see that the proportional elastic limit and sigma naught become material property. You can always find out this proportional elastic limit from the standard stress strain curve of the material. Due to unavailability of this data, one can take this value as 0.6. So, I should be interested to know how to compute the elastic buckling stress for the given problem, compare that with this ratio and check where do I fall in these two categories, and accordingly I pick up the psi factor, which is the adjustment factor given in the class on page 11 of ABS 2008. Once I know this, I will proceed further to find out the storm case utilization factor and check the adequacy. Let us move to the next step, step number 4, where we would like to compute the elastic buckling stress sigma EA as given by the section 2/3.3 of ABS 2008. Let us see the equation here, how we can compute sigma EA from the class of ABS 2008 from this equation. So, this is the equation given in class 2/3.3, where sigma EA will be a quadratic equation. We will solve this equation to find sigma EA, which is nothing but the elastic buckling stress for the given problem. So, sigma EA will be the unknown in my equation, and I naught and A are already computed in step number 1, which we already know for the given problem, and DCS in my case is nothing but the center distance from the CG to the shear center. For a circular symmetric section, this will be actually 0. So, this term goes away. So, what I wanted to know in this will be sigma E eta and sigma ET. Sigma ET is nothing but elastic torsion buckling stress, which is given by the expression So, the elastic buckling stress is given by this equation. In my problem, as I already know, the warping constant will remain 0 for a symmetric circular section. So, this term goes away, and I have all other values with me. E, Young's modulus of the material, I naught and K are values calculated in the first step, which are basic properties of the section. So, let me substitute here which will give me 0.769 10 power 5. Sigma E eta is the Euler's buckling stress, which is Euler's buckling stress, which we already computed in step number 3, and the value is so in the equation of elastic torsional buckling stress, I know eta En, I know Et, this term goes away, I know I naught and I know A. So, I will solve this quadratic substituting these values and try to get sigma Ea, which is the elastic buckling stress. So, let me substituting. Solving, I get sigma E as the lowest possible value, so in step number 5, let me compute the adjustment factor. Now, to compute the adjustment factor, I have got to check one condition, whether sigma Ea computed is greater than PR sigma naught. You have got to check whether this condition is satisfied. So, in my problem 8319.42 comparable with PR is 0.6 and sigma naught is 240, you will obviously see this value is much greater than this. If sigma Ea is higher than PR sigma naught, then the adjustment factor psi is given by an expression 1 minus 0.13 root of sigma Ea. So, I substitute them, I get 0.98. Therefore, the strength utilization factor for severe storm case, because I am looking for the problem where the platform is located in a severe storm condition. This is given by 0.8 of psi, in my case 0.8 of 0.98, which comes to 0.784. So, step number 6, I want to compute the critical buckling stress sigma Ca, that is the notation used in the code. Now, sigma Ca is given by two expressions, is directly equal to sigma Ea if sigma Ea is less than PR sigma naught, sigma F, or sigma F multiplied by So, depending upon the value of sigma Ea in comparison with PR sigma F, I will either select the upper equation to find sigma Ca, or I will select the lower equation to find sigma Ca. So, in this equation I already know PR, I already know sigma Ea, I have computed sigma Ea in the earlier step. So, what I wanted to know is what would be the value of sigma F. If you know this value, you can check the condition, select the appropriate equation and get sigma Ca. Sigma F is the minimum yield point stress for compact sections. Ladies and gentlemen, you will remember that already in the earlier step we established that the given cylindrical member is a compact section. So, sigma F will be a minimum yield point stress for a compact section. So, sigma F can be taken as equivalent to sigma naught, which is 240 Newton per mm square for my given problem. Now, you will know that sigma Ea will be much greater than PR into sigma F, and hence sigma Ca will be given by the second expression, which is sigma F of 1 minus PR of sigma f by sigma A. So, let us substitute these values back and compute So, substituting I will get this value as 238.4. This is 238.32. So, obviously in the next step we will check the adequacy of the design of this member under the subjected axial compressive force. So, let us establish the failure due to the buckling limit which says sigma A by n sigma Ca, is it less than or equal to 1 for safe conditions. So, let us see in my problem what is this value. Sigma A, we computed the direct compressive stress in the first step, which is 45.12, and n I have just computed in the previous step, which is 0.78, and sigma Ca is 238.32, which gives me a value of 0.24, much less than 1. So, the section is safe and adequate. Now, the question is safe in what? What is the safety level? The member is safe in axial compression and the member will not fail in column buckling. That is why in this step we check the buckling limit for failure. When the buckling limit is satisfied, the member is safe in axial compression and the member will not be failing in column buckling. So, ladies and gentlemen, this is one of the level of uncertainty what we have assessed, and always in design it is only checking of the adequacy of the given member. Just for summarizing, you already have been given a circular member of a specific diameter and of a specific thickness for a specific load carrying capacity. I am only checking the adequacy of the member using a specific code, using specific class. So, there are many empirical relationships being used in working out the adequacy. So, these are all considered as uncertainties. However, the level of uncertainties involved in checking these adequacies are far lower compared to experimental investigations carried on members. So, by following the detailed procedures as given by the code for checking the adequacy, it is always said and understood and established in the practicing professional that the formulae and equations recommended by international codes used for checking the design are always leading towards safe design and execution of the members. Thank you very much.